Hi, I'm Curt Frye. In this video, I would like to show you how to create a distance matrix for a traveling salesman problem. And then we'll go on to find a solution for the matrix as we've created it. The sample file I'm using, tsp_distance, is an Excel workbook that you can download from the link that I provide in the video description below. Over at the left, I have a set of 8 stations, and I have their X and Y coordinates. That is where they would appear on a map. So if we look at station 1, its X value is 13 and its Y value is 17. So we would go across to the right 13 and then up 17. Station number 2 is at 26 to the right and then 1 just above the bottom. And you can see the other distances there. We calculate the distance between 2 points, in this case, using the Pythagorean theorem, which I have here. And that is a squared plus b squared equals c squared. And you've probably seen this as the hypotenuse, or the square of the hypotenuse, of a right triangle is equal to the sum of the squares of the other two sides. So a squared, for example, might be the distance x squared. B squared would be the distance in y squared, and that would equal the square of the hypotenuse. And we do squares so that we can use subtraction to find the difference and always end up with a positive number. The formula we use is in cell F2, and I will double-click that cell to open it for editing, and you can see that I have typed a single quote mark at the front to the left of the equal sign. That is a way of indicating that I want the value to be treated as text rather than a formula. But when I press backspace to get rid of the single quote, then I have my lookup values. So what we're doing is finding the distance between the x coordinates and the y coordinates for the points that are listed in E2 and F1. And these are corresponding to station numbers, which are found over here. So what we can do is look up the x coordinate for, in this case, station number 1 by checking for the value in E2, looking in the array A2 through C9, and taking the value from the second column. So we would find 1 here in the leftmost column. That's how VLOOKUP works. And then in the second column, we would look in the same row and find the value of 13. We would then subtract the value for the second station, and in this case, that's also 1, and then subtract those two to find the difference and square the result. And we would do the same thing for the y coordinates. If you look at the cell references, you see that they are set up so that some of them are absolute and others are mixes of relative and absolute. So here we have E2, where the column name or column letter of E will not change. So we'll always look in column E regardless of which column the formula is in. And then for F1, which is up here at the top, the row will remain constant, but we are allowing the column to change. And the same thing for the y values, except here we'll be looking for the third column, which is the y values here, instead of the x. So with all that in place, I can press enter, and there is the value of 0. And before I copy the formula around, I will select the Pythagorean theorem and delete it. So from here, I can copy the formula and have it calculate the distance for each pair of values. I'll start by ensuring F2 is selected, and then drag the fill handle down until it covers F9. And there I have my distances for each pair. 1 and 1, which of course will be 0, 1 and 2, which is 21, continuing it down to 1 and 8. Now I can leave cells F2 through F9 selected, drag the fill handle over to the right, and here I have all of the distances between each pair of points, whether I look at the row first or the column first. And in fact, because I did it this way, we have a symmetric matrix. So going from 2 to 1 has the same distance as going from 1 to 2. That might not always be the case. For example, you could have construction or a one-way street going in one direction, but in this case, we'll assume that it is. You can become more confident that your calculations are correct if you have zeros along the main diagonal. So I have 0 between 1 and 1, 0 between 2 and 2, 0 between 3 and 3, continuing on to 8 and 8, which is also 0. Now we can create the rest of the traveling salesman model. So for that, I need to enter in the stations that we'll travel to. I'll put them in numerical order first, and then allow Excel to change that. So in cell C12, I'll type station 1, and in D12, station 2. Then I'll select C12 and D12 and drag over until I reach the end of my yellow cells, which are the changing cells in the model. So I have the values of 1 to 8. And now I can calculate distances between one point and the previous point. So I'll click D13 equal, and here I will do a lookup on the distance matrix at the top. For that, I will use the index function, and the array will go from F2 to M9, and be sure that you don't include the row and column headers in that data. Then I'll press F4 to make that reference absolute so it doesn't change, then a comma. The row number will be in cell C12, then a comma, and the column number will be in D12. Then a right parentheses and enter, and we get a distance of 21. So again, going from 1 to 2 is 21, so the lookup worked as expected. And I'll click D13, drag over to the right, and I have 1, 2, 3, 4, 5, 6, 7 distances. However, we need to go from 8 back to 1 to complete the cycle, and that should be included in the distance. And because the stations might change order, I will set K12 equal to C12. So in K12, I'll type equal, C12, enter, and there's the value of 1. And I will make that bold and centered. But it's not a changing cell. It's equal to the value in C12, so I won't make it yellow. However, I will copy over the distance formula. So going from 1 to 8 is 12. And I can see that value here. The total distance traveled will be the sum of all those values. So in E15, I'll type equal, sum, and then I'll select D13 through K13, right parentheses and enter, and there is the total. Now we can run our model. So I'll click cell E15, then go to the Data tab and click Solver, which I assume you have already installed. If you don't see it, go to the File tab, click Options, then among the categories, click Add-ins. Make sure Excel Add-ins is selected from the Manage list and click Go. Ensure that Solver Add-in is checked in the Add-ins box and click OK. And the Solver Parameters dialog box appears. The objective cell will be the total, so that is E15. You can see that here in the set objective. We want to minimize the value, and then the variable cells will be everything in yellow. So I'll click the collapse dialog button next to the variable cells list, and then C12 through J12. Remember that K12 equals the value in C12 to complete the cycle, so we don't need to include it. And in fact, we should not include it. Then I will expand the dialog box and add the constraints. So I'll click Add. The first constraint will be to ensure that all the station numbers are less than or equal to 8, because 8 is our highest number. So for the cell reference, I will have C12 through J12 less than or equal to the number 8. Click Add. Then the same cells need to be greater than or equal to 1. So I'll click there, greater than or equal to 1. Click Add. And now we'll create a constraint that you might not have created before, and that is to ensure that C12 through J12 are all different. So I will once again select C12 through J12, and then at the bottom of the comparison operator list, click diff, and the constraint is all different, and click OK. Next, we need to ensure that we have selected the correct solving method. You'll probably see GRG nonlinear. However, what we need is the evolutionary engine. So from the solving method list, I'll click evolutionary, and then click options. In the options dialog box, I'll click evolutionary, and at the bottom, I have require bounds on variables. You must make sure that this box is checked. So look for the check mark there to require bounds on variables. And that is what we did when we created the greater than or equal to 1 and less than or equal to 8 constraints. Those are the bounds on our variables. And everything else we can leave the same for now. I'll click OK. And there is the model all ready to go. So I'll click Solve, and we'll see how it runs. Looking at the bottom left, I see that we immediately have a better solution than the one we entered in at the start. And that value is 125. And we have about 25,000 subproblems that have already been tried. And the idea is, using some of the settings in the evolutionary tab of the dialog box, the options dialog, that we bypassed, we can control how the evolution works and also how long solver will look without improvement before it will end the search. So hopefully in just a few more seconds we will have an answer. There it is. So I have solver results, and I'll click OK. And I see that we are going from 1 to 4 to 3 and then to 6 to 7, 8, and 5, and then back to 1. So from there, we have a total distance of 125. And if we were to map that out, we would see that, yes, this probably is the optimal solution. I hope you enjoyed this video, and especially the first part about calculating distances between 2 points. If you liked it, please like the video and subscribe to my channel.